Let's look at some review problems associated with work and power. A force described by this vector acts on a 4 kg object. It moves the object from an initial position given by a position vector like that to a final position with position vector given by that expression, and it all happens in 5 seconds. Find the average power due to the force during that time interval. The first things to realize is that the force is a constant force. It is fixed in direction and magnitude. Note that we are interested in power. Now, power is defined as the amount of work done over a certain time interval. And work by constant force is simply the dot product of that constant force with displacement. And then take that, divide by the time interval. So let's first figure out what that displacement is. Displacement is given by the final position vector minus the initial position vector. That's the definition of displacement. Now the final position vector is given to be minus a 4i hat plus a 4j hat plus 6k hat. Subtract the initial position vector, which is given by that expression, 3i hat minus 2j hat plus 4k hat. So when you subtract this vector from that, you get the following. So let's look at the I hat component. Minus 4 minus 3, so that's minus 7 I hat. And then you have 4 j hat minus 2 j hat, so that's going to be plus 6 j hat. And then you have 6k hat minus 4k hat, that is 2k hat. Displacement is measured in the unit of meters. Having found this displacement, the next step is to take the dot product of the force vector and that displacement vector that we have just found. The force vector is given by that. Note the unit is newtons. So let's take the dot product. 4i hat plus 6j hat plus 7k hat dotted into minus 7i hat plus 6j hat plus 2k hat. So this is the force vector and this is the displacement vector. At this point I'm computing the work. So that's pretty simple. 4 dotted into minus 7, that's going to give you minus 28. 6 dotted into 6, that is a positive 36. 7 dotted into 2, that is a 14. And you're going to get 22 joules. Now, taking that 22 joules, and you divide by the time interval to accomplish this entire process, which is 5 seconds, you get the power. And that's going to be 4.4 watts. The unit watts can also be written as joules per second. Note, the work is computed in the unit of joules, and this is second. So it's either joules per second or watts. And that's the answer. Let's do a second problem. Graph below gives the acceleration of a 3 kg particle as it moves under the influence of a force from rest along the x-axis from the origin to x equals to 9. So this is the origin and that is the x equals to 9 mark. How much work has the force done on the particle when it gets to x equals to 6 meters mark? That means that point. Also find the speed of the particle and the direction of travel when it reaches this point. The first thing to integrate is this graph AX graph. A is acceleration in the units of meter per second squared, and position is in the unit of meter. We recall the fact that if you have force versus, let's say, the coordinate, and you have a graph like that, the area under the graph is the work. And we know work is simply F dx geometrically between two time interval, let's say t1 and t2. So t1 and t2. Now we know force is ma. So this can be written as mass times acceleration dx. Since mass is a constant, you can take that out of the integral sign and you get a dx. So what is this integral a dx? That is just the area under acceleration coordinate graph. What that means is, in order to compute the work done from this graph given, we have to compute the area from the origin until x equals to 6 and multiply that area with mass. And that's going to give you the work. So let's compute the area. The first area is this little triangle there. So let's call that area 1. So area 1 is the area of a triangle, half. Now this width is 1 times that length is 6. So that is quite simply 3. Next, the area of this rectangle. Let's call this area area 2. So area of a rectangle is pretty simple. This length, which is 3, because this is x equals to 4, that is x equals to 1, so this has got to be 3. Multiply with this length, which we know is 6, so that is 18. Now the third area, this one right there, area 3. So area 3, again, it's a right angle triangle. So the area of a right angle triangle is half times this width, which is, this point is 5, this point is 4, so it's 1, times, again, this length, which is 6. And that's going to give you another 3. And the final area is the triangle below the x-axis. Remember, we are computing the work done from x equals to 0 as the particle gets to x equals to 6. So this is the final area. Let's call that area area 4. So area 4, it's a right angle triangle, so it's half times, again, this width is 1, it's 6 minus 5, and the height is minus 6. So the area will turn out to be minus 3. There is a negative area because it's below the x-axis. So let's calculate all the area. Let's add them up. 3 plus minus 3, that is 0. And then you have 3 plus 18, that's 21. So 21 times mass, mass is 3. So it is 63 joules. So that's the answer for part A. Now let's do part B, the speed of the particle when it gets to x equals to 6. Let's use the work kinetic energy theorem. Work equals the change in kinetic energy, so the final kinetic energy minus the initial kinetic energy. Now we have computed the work done by this force as the particle reaches x equals to 6, so that is 63 joules. The final kinetic energy is the kinetic energy of the particle when it is at x equals to 6, and the initial kinetic energy when it is at the origin. Now we know it starts from rest, so that means the initial kinetic energy is 0. The kinetic energy at x equals to 6 is half times the mass, which is 3, times the speed of that particle at x equals to 3, which is what we want to find. And this is 63, and we can solve for that speed. And if you do the calculation, you get the speed to be 6.5 meters per second. And the direction of travel is along the positive x-axis. Problem 3. An elevator that weighs 4,000 kg has a load of 1,500 kg, and it's moving upward with a constant speed of 4 meters per second. What is the power of the force required? Let's do a quick free body diagram. So you have that elevator with the load, and of course the weight is 4,000 plus 1,500 kg, so that is 5,500 kg times gravitational acceleration. Now there is no acceleration, so A is 0 because it's moving at a constant speed of 4 meters per second. So the upward force, and there must be one, has got to be 5,500 G. Only then the net force is 0. And when the net force is 0, we know the acceleration is 0, as the case for this problem. What we are interested in is power. Note that power is given by work over time, and work is quite simply the force times a certain amount of displacement along the vertical direction, which we call the y-axis, over time. And we know what y over t is. That is just speed. So force times speed. The force is 5,500 times gravity, and the speed is 4 meters per second. And that's going to give you the power. And the power is 215,820 watts. And that solves the problem. Let's do another problem. A force acts on a 2 kg particle whose position is given by that function, so the position is changing with time. T is measured in seconds. What is the work done by the force from t equals to 0 seconds to t equals to 3 seconds? Note that work is given by the integral of force dx. But we have to change this integral from x integral to time integral. Now we know force is mass times acceleration. We know mass, but what is acceleration? How do we get the acceleration? Well, we have to take the derivative of that x function 2 times. So d2x dt squared. So that means the first derivative of x with respect to time will give you 2 minus 8t plus 3t squared. That's by differentiating this expression one time with respect to t. And if you do the second time derivative with respect to time, the 2 goes away, it's a constant. Minus 8t will become minus 8, and this one will become plus 6t. So let's substitute this expression in here. Your force is mass 2 times acceleration. Now it's minus 8 plus 6t. What about dx? So to this end we can write or rewrite this integral in a following way. F dx dt dt. Do you remember what dx dt was? It is 2 minus 8t plus 3t squared that we worked out a few minutes ago. Putting this and this in this integral, we will get the following. Work equals 2 times minus 8 plus 6t. So that's that. dx dt is 2 minus 8t plus 3t squared dt. Remember, the limit is from 0 to 3 seconds. Upon doing this integral, you will get minus 32t plus 76t squared minus 48t cubed plus 9t to the power 4. And the lower limit is 0, the upper limit is 3. Substituting the limit, you will get 21 joules. And that's the answer. And that solves the problem. If you find this video useful, please don't forget to share, like, and subscribe. This will definitely help the channel to grow. Thank you for watching.